All right, welcome everyone. Today, we're going to be talking about the ratio test. So this is another test. Got a few more to go. It's another test for determining whether a series is convergent or divergent. But this one it's going to prove to be very useful. So this is it's going to become kind of our go-to test for when we look at a series for convergence or divergence. And it's kind of fun. I mean, there's going to be a lot of canceling here. We're going to have fractions. We're going to be able to do a lot of canceling in the fractions. So it's kind of fun to do, anyways. So let's get started. So here's what the test says. It's called the ratio test, and so we're given a series sigma an that we're interested in. We want to know, can we add all these terms together? Is this series convergent or is it divergent? So does the sum not exist? That's what we're trying to determine here. Can we add all those terms together or not? And so what we're going to do is we're going to do this limit as n goes to infinity of the absolute value of an plus 1 over an. So we're doing this limit of this ratio. That's why it's called the ratio test. And we look at what happens to that limit. So there's four possibilities here. If that limit is less than 1, then the series is convergent. If the limit is greater than 1 or is infinite, then the series is divergent. So there's kind of two possibilities there. If the limit exists, if L is a number but it's greater than 1, or if the limit is just infinite, then the series is divergent. And then the last condition, sometimes the ratio test doesn't work. Unfortunately, that's the case sometimes. And this happens when the limit L is equal to 1. The test is inconclusive. So unfortunately it happens, but it is a nice, powerful test that we're going to be able to use. Just sometimes it can be inconclusive. So it's worth mentioning again. So there's really kind of four cases here. The limit L is a number less than 1. The limit L is a number greater than 1. The limit is infinite, or the limit L is equal to 1. And so we really want to stress that if L is equal to 1, then this test is inconclusive, meaning we don't know what happens to our series. It might converge, it might diverge. We just don't know. We don't have enough information. So what we would have to do then is go and use some other test. So the ratio test is inconclusive, so we would need to use some other test. So we have a whole kind of grab bag of tests that we can use. Might go back to the test for divergence, integral test, comparison test, the limit comparison test, the alternating series test. We have all those other tests to use. And that's what we'd have to do. We'd have to go back to one of those, maybe. Now, we do have this terminology here, absolutely convergent. We're going to see what this means in a few lessons. So kind of tuck that away. Really, the how we mostly use this test, though, is just testing for convergence. All right. So let's try an example. Just see how this works. So we're given a series here, sigma n equals 1 to infinity of -1 raised to the n minus 1 power times n to the 5th over 2 to the power n. So we're interested in determining whether this series converges or diverges. And we start this off by what? Well, the first step is really to kind of set up the limit that we're going to do and simplify as much as possible. So that's what we're going to do. First step is really to set up what we're trying to do the limit of. And that is this an plus 1 over an. So an here is everything that we're trying to add together here in our series. So it's just an is just everything that's right here. All right, so what's an plus 1? Well, it's our an term where we've just changed all of the n's that we see to n plus 1. So it's just the next term in our sequence, essentially. So an is the nth term, an plus 1 is the term right after that in our sequence. And so when we write this out, it's helpful to, a lot of times when we're dealing with series here, we have fractions. So when we would plug those into this, we would end up with fractions stacked on top of fractions. It can get a little messy. So a lot of times it's helpful to rewrite this as, not as a fraction, but as a product. So think of this instead as multiplication by the reciprocal. Just going to make things a little bit easier. All right, so let's actually start filling in what our an plus 1 is and what an is here. So first of all, let's just write out what an is, just to kind of have this in view. So an is just everything, every term here. Is just our general term of our sequence. So let's write it out. It's -1 raised to the n minus 1 times n to the power 5 all over 2 to the n. And I've just taken this power of -1 and moved it into the numerator here just to make this a little bit more consistent, just so we have a single fraction to worry about. All right, so this is our general term an. So when we set this up, we want to essentially change each of these n's that we see to an n plus 1. So let's do that. Every n that we see here, when we're trying to write out the next term in our sequence, we're just going to change each of these n's to an n plus 1. So we would end up with, in this -1 term, we would end up with n plus 1 minus 1, so it would just be -1 raised to the power n. In this n raised to the power 5, we would end up with n plus 1 raised to the power 5. So we just change that n to an n plus 1. And then in the denominator, instead of 2 to the n, it's going to be 2 to the n plus 1. So again, we just change that n to an n plus 1. And this is our an plus 1 term. So this whole thing right here, this is an plus 1. All right, so we have that done. Next, we just want the reciprocal of 1 over an. So take this fraction that's right here, our an, and just flip it. And we're going to put it right next door. So 2n was in the denominator. Now it's going to be in the numerator. And then the power of -1 and that n to the power 5 are now going to be in the denominator. So we're just flipping that fraction. And this is all inside an absolute value. All right, so we have it set up. We have the thing that we're going to do the limit of all set up. Now we want to try to simplify this. And that's the next part. Try to simplify this down as much as you can. Ultimately, we're going to do the limit of this as n goes to infinity. So if we can simplify this down, it's just going to make the limit calculation that much easier. And the way to simplify it down is to group like terms. So group them in their own fractions. So we have this -1 raised to the power n that's in the numerator. And then we also have this -1 raised to the n minus 1 that's in the denominator. Those are like terms. So we're going to group them in their own fraction. So the nice thing about multiplication when we're multiplying fractions is we can move things around back and forth between things that are in the numerator. We can move these around in between the fractions. Same thing in the denominator. We can move these around and break things up as much as we want. So the -1, the powers of -1 here are going to be in their own fraction. Then we can let's do the powers of 2. Put them in their own fraction. So we have a 2 to the n in the numerator, and then we have a 2 to the n plus 1 in the denominator. So those are like terms. They're both powers of 2, and we're going to put them in their own fraction. And then finally we have this n plus 1 to the power 5, and then this n to the power 5. Those are similar functions, so we're going to group them in their own fraction. All right, so we're just kind of rearranging things. It's kind of nice to do that. A little fun there. All right, now we get to start canceling. So first of all, we have these powers of -1 that are inside an absolute value sign. So no matter what the exponent is here, the absolute value sign is always going to cancel off these powers of -1. So we can essentially just cancel those out for free. Those powers of -1 are just always going to get canceled no matter what, because they're inside the absolute value. And then if we look at everything else is positive here. Powers of 2 are positive. N is a positive number, so these n terms raised to the power 5, those are positive. So once we cancel out these negatives, we can drop the absolute value sign. So we're left with 2 to the n over 2 to the n plus 1 times n plus 1 raised to the power 5 over n raised to the power 5. So a lot of nice simplifying there. Next, we can simplify these powers of 2. So if we look at this, there's n copies of 2 in the numerator, and then there's n plus 1 copies of 2 in the denominator. So when we cancel out all these powers of 2, everything's going to cancel out in the numerator, and we're going to have 1 left in the denominator. 1 power of 2 left in the denominator. So we're going to have 1/2. All right, so this is simplifying down. So this is where I always like the ratio test. This is my favorite test. Just because you get to group things all nice and tidy there, and then you get to do some canceling. This is a good one. All right, we got a little bit more to do. So this is going to be a common little, it's kind of like a trick, but it's helpful for when we actually go through and do the limit. What we're going to have here, we have these powers of 5. We're going to essentially factor off this common exponent and write this as 1/2 times, well, the 1/2 is going to just stay the same. We're going to factor off this common exponent and write it as n plus 1 over n all raised to the power 5. So when we have the same exponent, that's just one of our exponent laws that we can do. All right. And there's actually one extra little step here that we could do, and that's actually do the division. So sometimes when we after we do this, we can actually do the division. And what we end up with is n divided by n is 1. And then 1 divided by n is just 1 divided by n. So when we simplify this down as much as we can, we get to this 1/2 times 1 plus 1 over n raised to the power 5. And that's about as far as we can go in terms of simplifying. All right, so the next step is to actually compute the limit. So we're interested in doing the limit as n goes to infinity of the absolute value of an plus 1 over an. Now we did some work on the last page there where we really wrote this out, simplified it down. So let's fill in what our simplified version was. What was it? It was 1/2 times 1 plus 1 over n raised to the power 5. If I'm remembering that right, let me check. Yeah, that's what we got when we simplified it down. So all of this was just simplifying that down. Sometimes it's helpful to do this off to the side and then go to your main limit calculation. And that's what we're kind of doing. All right, so now we can actually calculate the limit. And we know this raised to the power 5 function. Power functions are continuous. So we can bring this limit inside the continuous function. So we can bring the limit in. And that's because raised to the power 5, that power function, is continuous. So we know limits work very nicely with continuous functions. And now when we do the limit of this is just something we can do. So that 1 over n is our c over infinity form. So we know that goes to 0. And then everything else is just constants. So what do we end up with? Well, we end up with the 1/2 in front. And then the limit of 1 is 1. The limit of 1 over n is 0. So we end up with 1 plus 0 all raised to the power 5. And if we simplify that down, you get 1/2. All right. So we were able to do the limit. Now we just have to actually state our findings. So state our conclusion. So we found that the limit L is equal to 1/2, which is, let's say that, which is less than 1. So we found the limit L was equal to 1/2, which is less than 1. And what that means is that by the ratio test, so it's always good, state which test you're using here. Our series is convergent. So when the limit L is less than 1, our series is convergent by the ratio test. So we're just stating our conclusion here. We found that the limit was equal to 1/2. It's less than 1. L is less than 1. So that's what we need for our ratio test to say that it's a convergent series. And that's it. So we're just calculating this limit of an plus 1 over an. Let's try another one. These are good ones to kind of practice. So let's look at example 2. We're going to determine if this series is convergent or divergent. So it's the sum from n equals 1 to infinity of n factorial over 3 raised to the power n times the square root of n. We're going to test this using the ratio test. And let's kind of get this started. So step 1, let's go through our setup here. So we know we're going to be looking at the limit of this gadget an plus 1 over an inside the absolute value. Again, it's usually helpful to not think of this as a fraction, but think of it instead as multiplication by the reciprocal. So that way you don't end up with fractions on top of fractions, and it gets a little messy that way. And to help us with this, let's write in what an is. So an is just the general term of our sequence here, the sequence that we're trying to add all the terms together. So really that's ultimately what we're trying to do. We're trying to add up all of the terms of this sequence, and we're trying to see, do we get a sum? Is the series convergent? Or does the sum not exist and the series is divergent? So the actual sequence we're working with here is represented by these terms here. So it's n factorial over 3 to the n times the square root of n. So that's the general term of our sequence. Now we're going to, we want an plus 1. So essentially wherever we see an n here, wanted to highlight that, not cross it out. There we go. Wherever we see an n up here, we're going to change that to an n plus 1. So let's write out our an plus 1 term. So we're going to have an n plus 1 factorial in the numerator. So we want to put parentheses around the n plus 1 because that's our number here that we're kind of doing the factorial of. And then what do we have in the denominator? Well, we had 3 to the n, but we're going to change that n to an n plus 1. So it'll be 3 to the n plus 1. And then we have this square root n, so it'll be square root of n plus 1. And so this is our an plus 1 term that we've just written out. All right, so what comes after that? Well, what comes after is the reciprocal of an. So we just take our an term that we wrote up here and we flip it. So 3 to the n times the square root of n was in the denominator. In the reciprocal, those are going into the numerator. And then n factorial was in the numerator, but when we flip it, it goes into the denominator. And so there we go. We've set this gadget up that we're ultimately going to do the limit of. So now our next step is to simplify this down. And we're going to use the same kind of strategy that we did. We're going to group like terms. Just makes the canceling and makes everything a little bit neater. So you can really see what's going to cancel and what won't. All right, so let's get this started. So let's start with the factorials. So we'll put the factorials in their own fraction. So we'll have n plus 1 factorial over n factorial. So n plus 1 factorial was in the numerator, n factorial was in the denominator. So we just kind of move those around and put them in their own fraction. Then we'll have multiplication. Then we have this 3 to the n and this 3 to the n plus 1. Again, it's multiplying fractions here. So we can move these terms around, split up the fraction as much as we need to. So we can have 3 to the n in the top and 3 to the n plus 1 in the denominator there. And then finally, one more fraction. Again, we're multiplying. Everything's being multiplied here. So the square root terms can go into their own fraction. So we'll have square root n over square root n plus 1. All right, there we go. Now let's start simplifying. And, well, we're going to be able to do some canceling here with the powers of 3. So let's do that. And while we're at it, if we look at this, n is positive. So n factorial and n plus 1 factorial are going to be positive. Powers of 3 are going to be positive, and these square root terms are positive. So everything in here is positive. So we can drop the absolute value sign. And then while we're at it, let's simplify these powers of 3. So there's n copies of 3 in the numerator. There's n plus 1 copies of 3 in the denominator. So everything's going to cancel except one of those copies of 3 that are in the denominator. We'll have one left over. So let's write this out simplified. So n plus 1 factorial over n factorial. We'll deal with that in a few seconds. The powers of 3 here end up simplifying into just 1/3. And then we have our square root terms. All right. So now we want to, let's actually work with those factorials. So let's remember what n factorial is. What is n factorial? Well, it's start with 1, and we multiply 2, then we multiply 3, and we keep multiplying numbers until we get up to n. That's what n factorial is. So what would it be n plus 1 factorial? Well, again, we'd start with 1, multiply with 2, multiply with 3, keep going, and we're going to keep going until we get to n plus 1. So if we're multiplying consecutive integers, to get to n plus 1, we would have to eventually multiply by n. So we would do 1 times 2 times 3, keep going. Then we'd multiply by n, and then we need to go one more. So we'd have times n plus 1. So it's sometimes with these factorials, it helps to write them out a little bit. And when you do that, you can see right here, this 1 times 2 times 3 up to n, that's just n factorial. So another way to think of n plus 1 factorial is n factorial times n plus 1. Because here's n factorial. Again, it helps to kind of write that out. So let's fill that in. Let's go back down here. We're going to keep simplifying this. So the n plus 1 factorial, we know we can write that as n factorial times n plus 1 all over n factorial. We have the 1/3, and then we'll deal with those square roots in a second. Now the n factorials cancel. Get those out of there. And what we're left with is an n plus 1 times 1/3. And again, that square root here is really a power function. So again, a property of exponents is that when we have the same exponent in both the top and the bottom of a fraction, and it's kind of applied to everything in both the numerator and the denominator, well, we can essentially factor off that common exponent. So we could write that as everything under one big square root. So n over n plus 1. And there we go. That's pretty good. I mean, maybe there's a little bit more simplifying we could do, but that's pretty good. So now I think we're ready to actually do the limit. So let's try it out. So we're going to do the limit of this. So we want to do the limit as n goes to infinity of this gadget an plus 1 over an. Let's use our simplified version. So it was, what was it? It was n plus 1 times 1/3 times the square root of n over n plus 1. All right. So when we look at this thing, the n plus 1 here, as n goes to infinity, this n plus 1 is going to go to infinity. 1/3 is going to stay a constant. So that's just approaching a constant. What's going to happen with the square root term? So let's kind of think about this one separately. So what about the limit of that square root term? Let's just think about that one separately. And when we do ones like this, we know the square root is continuous, so we can bring the limit inside the square root function. So we have a big square root and then the limit underneath. So we're going to do the limit of n over n plus 1 as n goes to infinity. Now we just use our standard when we have these rational expressions like this. We go to our standard technique of dividing everything by the largest power of n that we see in the denominator. So in this case, the largest power of n is just n. So we're just going to divide everything that we have here by n. So we'll get n over n in the numerator. And it's not looking good. So we'll get n over n in the numerator, n over n in the denominator, plus 1 over n. And we're doing the limit as n goes to infinity. And now the n over n's just cancel. So it ends up being the limit of 1 over 1 plus 1 over n as n goes to infinity. And that 1 over n, that's one of our c over infinity forms, so that goes to 0. So what do we end up with? We end up with the square root of 1 over 1 plus 0, which is equal to 1. So what's happening here is this square root term is getting really close. As n goes to infinity, the square root term is getting really close to the number 1. The 1/3 is just staying a 1/3. But this n plus 1 term is getting really big. It's getting really large positive. So overall, this entire expression here is going to infinity. So this is equal to infinity. It's an infinite limit. And so we needed to check this. If this was going to 0, well then this would have been an indeterminate product and we would have had to do, something else. But the fact that this limit, the limit of the square root term does exist and it's equal to a non-zero number, really that's the important thing here. It's a non-zero number. If it was 0, then we would have had an indeterminate product and there would have been more work required. But the fact that this is equal to 1 means that overall, these terms here are just approaching a number, finite number, but this n plus 1 is getting really big. And so when we have a really large number multiplied by something that's not 0, or not getting closer to 0, the result is infinite. All right, so now we can just state our conclusion. So since L is infinite, it's an infinite limit, this series diverges by the ratio test. Again, just get into that habit of stating which test you use. It's good to do that. And we've stated our result here. So our series diverges. All right. So one kind of last thing to mention. So this is really the ratio test. I think we have enough now, seen enough examples where we can really just make use of this ratio test. It's a handy one. It's going to be the test that we kind of fall back on most of the time. There are some unfortunate times, though, when the ratio test is inconclusive. So that happens when L is equal to 1. And what that means is, it means we can't say anything about the series. The series might converge, it might diverge, we just don't know. The test is inconclusive. And for p-series, the ratio test is always inconclusive. So this is not uncommon where the ratio test might just not work out. It might be inconclusive. And as an example, if we looked at the p-series 1 over n squared, and you were to try the ratio test would be inconclusive. Try it out for yourself. Try going through the ratio test. You would get the limit is equal to 1. But we know this is a p-series with p equal to 2, so we know this is convergent. So since our p-value is greater than 1, it is convergent. The ratio test does not tell us that, though. So the ratio test, if we were to do it, the ratio test would show this is inconclusive, which anything we don't know. It might be convergent, might be divergent. Ratio test doesn't tell us anything. We just know from previous lessons that this is actually a p-series. The p-value is 2, which is greater than 1, so it's convergent. Try it out with the harmonic series. 1 over n from n equals 1 to infinity. Again, the ratio test would be inconclusive here. So try it out. Try that for yourself. Run through the ratio test. See what would happen. But we know what this series does regardless of what the ratio test tells us, because again, this is a p-series. With p equal to 1. And we know when the p-values are less than or equal to 1, the p-series diverges. So this just shows that if your ratio test is inconclusive, you don't know what happens. You might have a series that's convergent. You might have a series that's divergent. So in that case, if the ratio test is inconclusive, you would have to go back and try some other test. In this case, we've just identified that these are just p-series. So we know what they're doing already. All right. So that's going to do it for the ratio test. The next one we're going to look at next time is kind of related. It's called the root test. So it'll feel kind of similar once we get into that one. So we'll see you then. Bye-bye.